Welcome, dear students. Now we discuss Unit 4 2021 CC-10 Mechanics paper semester 4. This question paper Unit 4 question 5a. A particle is projected with velocity u at an inclination alpha acute above the horizon in a medium that resists the motion by a force kV per unit mass, where v is the velocity of the particle. Prove that the equation of trajectory is y equal to this, where x and y are respectively the horizontal and vertical upward coordinates of the particle measured from the point of projection. Let a particle of mass m is projected from origin O with velocity u at an angle alpha with the horizon positive x-axis in the anticlockwise sense. So this is the initial component u cos alpha horizontal component, and this u sin alpha vertical component at t is equal to 0. At time, anytime t, and p is the position of the particle of mass m, and here this particle is moving in this direction. So resistance, this is the direction of velocity is this. So resistance, air resistance is mk into v in this direction, and this weight is mg, this downward direction, particular downward direction, and this resistance force mkv. This angle is psi. This is the tangent with the x-axis. This angle is psi, so this angle is psi. So this component is mkv cos psi, and this um, in this direction, and mkv sin psi in this particularly downward direction. So equations of motion of the particle is given by along the x-axis is m d2x dt square is equal to minus mk x dot. Actually, this m minus mk x dot means mkv cos psi. This is the minus because this minus is this velocity, this m x double dot d2 dt square, and the velocity v. So this component, this force this along the x-axis, and this is the negative direction of the x-axis. So minus mkv cos psi. Now this v is ds dt and cos psi is ds dx. So we get dx dt. So dx dt equal to x dot. So we write here minus mk x dot. And this vertical component, this the v, so this force is this, and this m y dt square equal to, and force p is equal to mf. So this Newton's second law, by Newton's second law, equation of motion is and so mass into acceleration, and this force is this minus mky dot because this upward direction, so downward direction is negative direction here. This, so mkv sin psi, actually mkv sin psi means v means ds dt and sin psi is dy dt. So actually mk dy dt, that is mky dot, this negative sign here, and because it's downward direction, and this another force with the weight particularly downwards, which also is a negative direction towards O, origin O. This, so this is the minus negative sign here. And from equation 1 we get this dx dot d dt of dx dt by x dot, this x dot minus k, cancel m from both sides, so minus k into dt, and integrating we get log x dot means dx dt to the base e minus kt plus log c1 is integrating constant to the base e. So x dot equal to c1 e to the power minus kt. Initially at time t equal to 0, this x dot equal to u cos alpha, this is the horizontal component u cos alpha. So from this we get this x dot equal to put here this x dot equal to u cos alpha and this t equal to 0. So C1 equal to u cos alpha. So we write from this x dot equal to u cos alpha e to the power minus kt, equation 3. Again integrating this, so dx dt, so we get integration dx u cos alpha integration e to the power minus kt dt. So after simplification we get this plus c2 constant. Initially at t equal to 0, x equal to 0, and this put, so from this c2 equal to this, hence x equal to u cos alpha by k bracket 1 minus e to the power minus kt, equation 4. And from 2, equation 2, this my double dot equal to this. So from 2, dt of dy dt equal to minus k dy dt minus g, cancel m from both sides. So from 2 we get this, so dt of dy dt equal to minus common bracket k dy dt plus g. So we can write d of k dy dt plus g whole divided by k dy dt plus g, because this k d of k dy dt plus g, so this actually this equal to k into dy dt. So this k and this k cancel from each other, k not equal to 0 quantity and non-zero quantity. So this quantity is log of ky dot plus g minus kt plus log c3 is integrating constant. And initially t equal to 0, y dot equal to u sin alpha vertical component. So from this value of c3 equal to this. So putting the value of c3 in this equation, so yet ky dot plus g equal to this. Integrating this 5, we get this. So this constant with integration c4, and again applying initial condition t equal to 0, y equal to 0. So c4 equal to this, and putting this value of c4 in this equation, we get this ky plus gt equal to this equation 6. And from 4, equation 4, this 1 minus e to the power minus kt equal to kx by u sine cos alpha. So this kx by u cos alpha, so t equal to this taking log to the base, so 1 minus 1 by k log bracket 1 minus kx by u cos alpha. And from 6, so this equal to ky plus gt, the value of t, from this t, put the value of t here, and this ku sin alpha plus g by k, and this 1 minus e to the power minus kt equal to kx by u cos alpha. So put this, cancel, and after simplification we get y equal to this, and this is the required equation of the path proved. Question 5b. A mass m hangs from a fixed point by a light string and is given a small particle displacement. If L be the length of the string when the system is in equilibrium and n be the number of oscillations per second, then show that the natural length of the string is L minus g by 4 pi square into n square. Let us consider an elastic string of natural length small a, and this is equal to natural length, and which is fixed at the point O and hangs vertically. And a mass small m being attached to the end A hangs in the equilibrium, and this position when we attached here as a small m mass at this point, this is the equilibrium position after attach this mass m. So this initial length is A, and this equilibrium position length is this extension E. AB is the extension after hanging the mass m. So OB equal to, this equal to L, actually L means A plus E. The extension E of the string is given by this equal to mg equal to lambda AB by OA. This AB is the extension divided by OA. OA is the initial length. So lambda E by A. So E equal to AM G by lambda, where lambda is the modulus of elasticity and the tension of the tension in the equilibrium position B is lambda E by E. This is the tension at equilibrium position B. We call this point position B is the equilibrium position. Now, if the particle is displaced vertically to the position P such that Bp equal to x, and this is the we displace this point B to P, this distance Bp equal to x. Then the tension T of the string in this position P is given by T equal to this lambda into this AP divided by this extension from A to P. So this extension and initial length is OA. So OA is the small a here. So AP equal to E plus x because this length is AB is E and this is x. So E plus x. So we get mg plus lambda x by a. We put here lambda E by a equal to mg. So tension T at this position P equal to mg plus lambda x by a. Hence, the resultant force acting on the particle in the direction BP is mg minus T. Mg minus BP in the direction BP, mg minus T. And minus T is the upward direction. So mg minus the value of T is this, actually minus lambda x a. The equation of motion of the particle is equal to m dq dt square equal to minus lambda x a. Actually, the resultant force on the particle at this position P. So we get this the second order differential equation. This lambda m a are all positive quantity. So this minus this lambda m a by into x, equation 3, which shows that this particle execute is simply harmonic motion vertically with its position of equilibrium B as the center of oscillation. The time period of motion is twice pi root over ma by lambda, because we know this dq dt square equal to minus mu x for simple harmonic motion. The time period is 2 pi by root mu. So from equation 3, time period is this twice pi root over ma by lambda. Actually, from 1, this ma by lambda equal to this ma by lambda e by g. So put here this e by e root over e by g. In the given problem, n be the number of oscillations per second. So per second, in 1 second, number of oscillations, n oscillations. So n oscillations occurs in 1 second. So one oscillation occurs in 1 by n second. It is called the time period t. So this is the time period 1 by n here. So obviously this 1 by n equal to twice pi root over e by g. So root e equal to root g by 4 pi n and e equal to g by 4 pi square n square. Now L equal to a plus e. So a equal to L minus e. This equal to L minus e means g by root 4 pi square n square. So this is the required natural length, this a of the string. Next question. Question 6a. A particle describes a path which is nearly circle about a center of force under the action of central force phi at its center. Find the condition that the motion may be stable. Also find the apsidal angle in this case. Let a particle of unit mass describes a path which is nearly a circle under the action of central force phi u, with the center of force at the center of the circle with u equal to 1 by r. The differential equation of the path is d2u d theta square plus u equal to phi u by h square into u square, equation 1, where h is the angular momentum per unit mass of the particle about the center of force. If the path be a circle of radius 1 by c, r equal to 1 by c, that is u equal to 1 by r equal to c, so v equal to c. Therefore, du d theta equal to 0 because c is constant, and d2u d theta square equal to also 0. And from 1, we have this 0 plus c equal to c pi c by h square into c square. So h square equal to pi c by c cube, equation 2. Now let the particle be slightly displaced from the circular orbit in such a way that h remains unaltered. And let u equal to c plus x, where x is very small quantity, and this from 1 we get d2 d theta square c plus x plus c plus x. From 1 this u we put here u equal to c plus x, put here c equal to c plus x, and pi c plus x h square u square, so c plus x the whole square. So this c is constant, so d2x d theta square plus c plus x. So we get right pi of c plus x c cube by pi c equation by 2 value of h square. So this is equal to pi c by c cube. So we get c cube by pi c plus x, and this taking common c square, so 1 by c square is equal to 1 plus x by c whole square, so this 1 minus plus x by c whole to the power minus 2. And expanding this pi c plus c Taylor's expansion about the point c, we get this, and binomial theorem expanding this, we get these terms. And multiplying this c by pi c into pi c into 1 into x into 1, so this pi dash c, and this, and pi c into minus twice cx, this, and when we multiply this and this into this, so x square, so x is small, so this we omit this x square, x cube, and x to the power higher orders of x, omit this term. So we write here only up to the first order term because the x is small quantity. So this multiplying this c plus c into pi dash c by pi c into x minus twice x. So this equal to d2x d theta square, and this in the left hand side c plus x, so cancel this c and adjusting this minus 3x, so we get common, minus taking common is 3 minus c into pi dash c by pi c dx. Now if this quantity is positive, so we get this n square c positive quantity, then d2x d theta square equal to minus n square x, and so this is the synchrotonic motion equation, and the required solution, general solution, is this x equal to a cos n theta plus b. A, b are constant of integration, arbitrary constants. Then the approximate value, approximate path of the particle is given by u equal to c plus a into cos n theta plus b, because u equal to c plus x. So put the value of x here. So now cos theta lies between minus 1 and 1, and so we get this adding c, so c adding first multiplying a, so minus a less than equal to a cos theta, a cos n theta plus b less than equal to a, and then adding c, we get this c minus a less than equal to c plus a. So u since x is small, so a is obviously this a, x is small, so obviously a is also small, and this shows that the orbit of the particle will remain nearly circular orbit. A is small, so circular orbit, nearly circular orbit, so hence circular orbit is stable after disturbance x. If this quantity is negative quantity in the equation 3, this quantity is negative quantity, then the equation 3 becomes d2 is d3 is equal to m square x square. I put here minus m square equal to this in its real quantity. And the general solution of this, e1 e to the power n theta plus b1 e to the power minus m theta, e1 b1 are constants, identity constants. This shows that if theta increases, x also exponentially increases. Hence, x is not always small and the orbit does not continue to nearly circular. Thus, the circular orbit is unstable in this case. And last case 3, if this quantity is equal to 0, so d2 is d3 is equal to 0, and this integrating twice, we get x equal to a2 theta plus b2. This a2 b2 are arbitrary constants. If theta increases, then x is also increases, and so the circular motion will be again unstable here. So the nearly circular orbit will be stable if this quantity is positive, that is if c phi dash c by phi c is less than 3. Now, for the second part, apsidal angle in the nearly circular orbit. When the nearly circular orbit is stable, that is 6 volts, we have u equal to c plus a into cos bracket n theta plus b, where n square equal to 3 minus c phi dash c by phi c. And the apsidal distance is given by d theta of u equal to 0. That is this quantity after differentiating this, so this is equal to sine n theta plus b equal to 0. That is n theta plus b equal to k pi, k equal to any integers 0 plus minus 1 plus minus 2 and so on. So theta equal to k pi minus b by n. And the difference between two successive values of theta, that is k plus 1 pi minus b by n minus k pi minus b by n, that is pi by n. So n equal to, already find this, the value of this pi by n equal to root over of 3 minus c phi dash c by phi c, because we put here n square equal to this, so n equal to root over of this. And this is the required apsidal angle of the path. Note that apse means this is the apse of particle on a certain orbit, is a point in the orbit where the distance of the point from the center of force is either maximum or minimum. In apsidal distance, the distance between the apse and the center of force is the center of force is here, say, and this is the orbit of the path is, and this point A and B are apse. And this maximum and minimum distance, and this the distance between the apse and the center of force, that this is the R max, and this say R min, maximum minimum distance, this absolute distance. And apsidal angle, the angle subtended at the center of force by two consecutive apses, is called apsidal angle. So this is the apsidal angle. And at an apse, the radius vector is perpendicular to the tangent. This radius vector is perpendicular to the tangent. Next question. Question 6b. A particle of mass m is projected vertically under gravity with velocity lambda v. The resistance of the air being mk times of the velocity, so that the greatest height attained by the particle is v square by g into lambda log 1 plus lambda, and after time t, this where v is the terminal velocity of the particle. Let a particle of mass m be projected vertically upward with velocity lambda v from O, chosen as origin. No figure, no marks. Here lambda is positive quantity, positive constant, and capital V is the terminal velocity of the particle. The air resistance is equal to mk into velocity, where k is the positive constant. At any time t, position of the particle is p with mass m at a distance x from O. and this distance of P is x, and v is the velocity of the particle P. The equation of motion of the particle is m dv dt mass into acceleration is equal to force. Here mg vertically downwards and mk towards O, so negative, and resistance force mkb vertically downwards towards O, so this is negative. So equation of motion is this: dt of v equal to minus bracket g plus kv. If capital V be the terminal velocity of the particle, then capital V is the maximum downward constant velocity with this acceleration dv dt equal to 0. And for the downward velocity, this particle at this point, this particle is downward, so V is in this direction, mg is in this direction, but mkv is resistance force is opposite to the velocity in this direction. So dv dt and m dv dt equal to minus g plus and kv, minus g to kv. This minus this towards O, and mkv is the away from O, is plus kv. So when v equal to capital V, dv dt equal to 0, acceleration is 0. So this equal to k equal to g by capital V from the terminal velocity. Then equation 1 becomes putting this value k. Equation 1 is this. I put the value of k from these 3. We get equation this, and minus g by capital V dx equal to, initially at x equal to 0, v equal to lambda v. This is the given that is the lambda v is the projected vertically under the gravity with velocity lambda v is the initial velocity lambda v projected vertically upwards. So integrating 0 to x and integration lambda v to v to dv. So after simplification, we get this. At the greatest height at the point A, v equal to 0 and x equal to, say, capital H. So at this point A, x equal to capital H and t time t equal to capital T, say. So from above we get put x equal to h and v equal to 0 here. So from this we get capital H equal to this, and this is the maximum height of this particle and the required distance of the greatest height at this point. And the second part is this time. So from equation 1 we get dt equal to minus dv by g plus kv. Initially t equal to 0, v equal to lambda v. So integrating limit 0 to t, this lambda capital V to v minus this. So after simplification, t equal to this. At the greatest height A, when v equal to 0 and t equal to capital T, so we put t equal to capital T and v equal to 0, or v equal to 0. So we get required time to attain the maximum height is v by g log to the base 1 plus lambda. Thank you for watching.